turn out the We're very pleased this afternoon to have Dr. Vladimir Dobrokhotov here. He's here from the University of Louisville, where he has a research appointment. He has his undergraduate degrees from the University of Nizhny Novgorod in Russia, and has a PhD from the University of Iowa. Welcome.
Thank you. Welcome everybody. So I represent here Electro-Optics Research Institute and Nanotechnology Center, University of Louisville. The subject of my talk today is self-assembly of nanostructures for chemical, biological, and mechanical sensing. So first of all, I'd like to tell you a few words about self-assembly, because people use this term everywhere, self-assembly, but typically nobody knows what it is. Some people think that it's some kind of voodoo magic. Some people say, especially old theorists, they say that self-assembly, using the term self-assembly, is an excuse for not knowing things. So if something happens, if we observe some effect, but we don't know what it is, we say, oh, it's self-assembly, right? So I looked up some definitions on web. You can see that first one, it's like, I would say self-assembly is a power of God for the most part. Second one is more related to my understanding of self-assembly. And I would give you a broad definition of how I understand self-assembly. Let's say under certain conditions, we have thermodynamically favorable forms and shapes of matter. And matter, condensed matter, takes these forms and shapes to minimize energy and go into stable equilibrium. This is basically self-assembly. So, more details about self-assembly and about my talk today. First part of my talk will be about self-assembly of metal gallium alloys. So, as you can see, they take a wide variety of different morphologies. So, let's say this is an alloy of gallium with palladium. This is with silver, 2 slides. Next one with iron. This is also iron. See, sometimes it takes the form of nanotubes. This is with platinum nanoplates. And this is with aluminum. So I'm going to talk about the formation of these nanostructures and how they can be applied in biological and medical sensing. Next part will be probably the major part of my talk about self-assembly of semiconducting nanowires and self-assembly of gold nanoparticles on the surface of semiconducting nanowires. This is called hybrid nanostructure, hybrid of nanowires and nanoparticles. They have a wide variety of practical applications, in particular for gas sensing and fuel cell technology. And the final part of my talk will be about some preliminary results on atomic graphene, layers of atomic graphene. I would like you to consider this last part as a nanofabrication part, although we have some measurements. Most of them don't have detailed theoretical explanation, just rough ideas about them, but they're really interesting from the point of view of making devices and nanofabrication. So let's start from metal gallium alloys. The origin of this experiment is really really interesting because how we obtained all these nanostructures originally. One of our undergraduate students was making experiments on propagation of liquid gallium on different metallic foils, just basically measuring speed of propagation to find the diffusion coefficient. And after he coated the metallic foils with gallium, we etched them with hydrochloric acid and decided to take a look what happened with the surface of the ASEAN. And what we found out that gallium basically reacts with metallic surfaces and forms different structures, different nanostructures. Starting from cubotahedrons, this is quasi-spherical shapes, then metallic rods and bars, so these are hexagonal rods, these are rectangular bars, and plates. So as I mentioned before, this is a case of reaction with palladium, this is silver, this is iron, and this is platinum. So the nature of these morphologies, I mean, people are trying to study what is the origin of these different morphologies and what leads to the formation of cubotahedrons or nanobars. But general principle is the following. Everything is determined by the speed of reaction. If speed of reaction is high, let's say in the case of palladium, we have lots of atoms of metal, atoms of palladium available in the solution. Basically, gallium is a solvent for metal. In this case, nanocrystals take form of cubotahedrons because it's a thermodynamically favorable form to minimize surface energy. So as you know, analogy to this, if you put a droplet of water on the surface, it will take a shape of quasi-spherical shape, basically, or spherical segment, because of thermodynamic equilibrium. In the case of silver, let's say, the reaction is significantly slower than in the case of palladium, and in this case, it's possible that we have predominant contribution of one of the directions. In this particular case, it's direction 100 in the crystal planes. And this is so-called kinetic control, proof under conditions of kinetic control. If we reduce speed of reaction or reaction rate even more, and this is the case with platinum, crystals take shape of nanoplates. But again, this is just brief explanation of what happens. To understand it clearly, people write sophisticated programs involving density functional theory to explain formation of different crystals. Experimentally, this is interesting, but it doesn't have too many practical applications right here because it's just a formation in the form of film, and we cannot really separate them easily. But what we can do, we found out that some of these nanocrystals can be synthesized directly on the AFM tips, so on the AFM probes. And these are two examples. Let's say AFM probe with platinum nanoplate at the end, or AFM probe with a silver gallium nanoneedle at the end. Okay, so now I'm going to talk about primarily about silver gallium aluminum nanoneedles because they have a lot of different practical applications. Process of synthesis is pretty straightforward. We coat AFM probe with silver, and then using nanomanipulators, Zyvex nanomanipulators. This is a 4-probe stage with piezo elements. Inside the scanning electron microscope, we dip our AFM probe into a droplet of molten gallium. It's very easy to do because a melting point of gallium is very low. It's around room temperature. And after keeping it in the droplet for a while, we withdraw